Hello everyone, today let's solve the problem Ehab and the expected GCD problem, right? So this was asked in the Codeforces round 563 for the division 2, right? So you can just go through the question. I'll just summarize the question so that it will be easier for us to solve the problem. Very easy problem, not very easy basically, kinda difficult, kinda easy problem, right? So you can just go through the problem. I'll just summarize so that it will be easier for us to solve the particular problem, right? So this is fine. Now let's see what the question states here. Just give me a second, 1 second. Yeah, so we have been given n, just remember this one, we have been given n for the permutation p of 1 to n, right? For the permutation p of 1 to n, right? So we have been given n for the permutation p of 1 to n. So we have to define here g underscore I, this is nothing but the g equals GCD, just give me a second here. Yeah, g equals, so this one GCD of this one p1 to pi, right? Based on the input rate, basically p1 to up to pi, right? So this is fine. We have to define gi is equal to GCD of p1 to pi. Let f of p be the number of distinct values among g1 to gn, right? Again, let, so this is one part. Now let f of p be the number of distinct values among g1 to gn, right? Among g1 to gn, right? So let f max of n be, so this is second part, and the third part is let this one, what do we call, f max of n, right? So let me go with here f max of n, right? So let f max of n be the maximum possible f of p, right? So this be the maximum possible of f of b, right? So f of p, right? So what we need to do, these are the three main points, right? So what we need to do here, we have to count the permutations p with f of p is equal to f of max of n. So what we need to count here, we need to count, so let me write here, we need to count the permutation p with f of p here. This is equivalent to the f of max here, right? So this is equivalent to the f max of n, sorry, not f of max, so the f max of n, right? So modulo 1e9 plus 7, nothing but 10 to the power of 9 plus 7, right? So the modular value they have given here, so we have to make use of this one, 10 to the power of 9 plus 7. We shouldn't forget this, so we have to make use of it, right? So this is fine. We have to return the count for given n, right? So we have to return count for given n, we have to return count for given n. This is fine. Now this is the question, so let me read this one loudly one more time. Let's try to understand this one, right? So we have been given n here, right, for the permutation p of 1 to n. So that's what I have written here. We have to define g underscore I, nothing but g here equals GCD of p1 to pi, right? So this is fine. This is one part. Next, let f of p be the number of distinct values among g1 to gn, right? Among g1 to gn. This is also fine. Now let f max of n be the possible maximum possible f of p. This one, let f max of n be the maximum possible f of p. So we need to count the permutations p with f of p equals f max of n modulo 10 to the power of 9 plus 7, right? So we need to return this one, count for the given n, right? So we need to return count for the given n. Basically we need to count permutations p with f of p equals f max of n, basically, right? So also we need to use the modular value. Just remember this one. This is the question, basically simple, right? Now let's do one thing. Let's come to the input output part. Just give me a second, 1 second. So here n we have been given 2, right? So this is n, right? So n we have been given 2, and the output that we need to get here is 1, right? So this is simple, right? So first thing, so this one is bit easy. So let's do one thing. Let me discuss the approach here itself, right? So let's go with the key observation, basically. So here the sequence of the prefix GCDs is non-increasing, non-increasing, it is not increasing, right? So the sequence of the prefix GCD is non-increasing, and every time it strictly decreases, it becomes a divisor of the previous value. Just remember this, right? So the maximum length of the distinct GCDs that corresponds to the longest chain of divisors that is formed by repeatedly multiplying small primes will exceed n, right? So basically whatever the code that we build, right, so the basically whatever the code that we write will build the chain by repeating 2, right? So 2 in the sense m equals floor of log to n times, and optionally adding a 3 if 3 into 2 to the power of m minus 1 is less than or equal to n, right? So just keep this in mind. So each ordering of these multiplicative steps corresponds to the candidate GCD chain. For each chain, it counts arrangements of numbers that produce exactly that chain using the DP multiplying combinatorial ratios, right? So finally it counts for all the unique orderings, right? So this is fine. So let's consider n equals to 2 here. In simple terms, we are going with the first this one itself, this input. So output that we need to get here is 1 basically, right? So for GCD, this one, what do we call? We have considered n equals to 2. Let's go with the step-by-step explanation. Permutations of, we have to go with the permutations of 1 and 2, because n we have been given 2. We have to go with the permutations 1, 2, right? So 1, 2. So permutations of 1, 2 are here 1, 2 and 2, 1. We know this one, right? So this is the permutations of 1, 2 basically, right? This is fine. Let me represent this one within the square brackets, right? So the permutations of 1, 2 is 1, 2 and 2, 1. This we know, right? So this is fine. For 1, 2, for this one, for first one 1, 2, so G1 is 1. So right, so G1 here, G1 is 1. For 1, 2, G1 is 1, and G2 is nothing but GCD of 1, 2, right? So GCD of 1, 2, nothing but here in this case it is 1 itself. GCD of 1, 2 is 1 itself, right? So here distinct GCDs will be 1 and f of 2 will be 1 as well, right? So this is one distinct GCD is 1, and this one we have to go with a if I remember correctly, we have to go with this one, f of p equals f max of n, right? Modulo value, this one. So now distinct GCDs is 1 and f of 1, 2 is 1, right? So this is fine. Now let's go for the 2, 1. So we have two permutations, right? So now let's go for the 2, 1. Here this one, G1 will be 2 basically, and G2 will be GCD of 2, 1, right? So GCD of 2, 1 is again this one, 1 itself. GCD of 2, 1 is again 1 itself. Now this time distinct GCDs will be 2, 1, right? So for this one actually distinct GCDs were this one, only 1, right? This one is distinct GCD. So I'll just write here DGCD, nothing but the distinct GCD. And f of 1, 2 is also 1 was 1. For this one distinct GCD would be 2, 1, right? So this one distinct GCD would be 2, 1, right? So this is fine, and f of 2, 1 will be 2 itself. So here in this case for the second one, so this one f max of 2, just give me a second here, let me write this one here. So here in this case f max of this one, n we are going, right? N is nothing but the 2 here. F max of 2 is nothing but here 2, right? So f max of 2 is nothing but the 2, and only one permutation achieves it here, right? So only one permutation achieves it. This one, the second one, 2, 1 permutation, this achieves it, right? So again I am telling f max of 2 is 2 and only one permutations achieve it, right? So hence the answer, only one permutation achieves it here. So the answer would be 1 here, because we have to return the permutations, how many number of permutations achieved it, that one we have to return in the form of output, right? So only one permutation achieves it, f max of 2 equals to this one, only one permutations achieve it, and this one we have to return in the form of output. So output that we got here is 1, right? So basically the code's dynamic programming or counting evaluates exactly the combinatory combinatorial choices, and the output will be quite obviously 1. And one more thing, we will be making use of the DP along with this one, numerical calculations, right? So let's see that one while we write the code directly. So we will be making use of the DP, dynamic programming. Just remember this one, right? So certain things we need to cache, and those things, let's see that one directly within the code itself, right? So now here the output that we got here is 1, because f max of 2 is nothing but it is equivalent to the 2, and only one permutation achieves it. Which permutation? This one, 2 comma 1, this achieves it. So output is 1, right? So the output that we got here is 1, which is equivalent to the output that they have mentioned for the example 1 or the input 1 within the question, right? So our approach works absolutely correct in this case. So this is the approach that we will be going with, right? So I insist you to try out for the input 2 or the input 3. For the input 2 you have to get the output 4. For the input 3 you have to get the output 120, right? So I insist you to try out for these examples so that you understand the question even better, right? So this is fine, man. Now we are done with the approach. So let's, as we are completely familiar with the approach part, let's quickly discuss the complexities part. So what will be the time complexity here? So the time complexity would be big O of n, right? So why the time complexity here would be big O of n? So basically the time complexity would be big O of n. So why it is big O of n here? Because we will be going with the factorial pre-computation, right? So factorial pre-computation dominates here. The permutation or the DP loops, so we'll be making use of the DP, as I have said. The permutation or the DP loops runs in big of logarithmic n steps with a small overhead. So factorial pre-computation domination, it will dominate basically, right? So in this case the overall time complexity would lead to big of n. So what would be the space complexity here? The space complexity would lead to big of n as well, right? So why the space complexity here would be big of n? So factorial array, nothing but the FACT, right? So factorial array FACT, so this one of size n plus 1, factorial array of size n plus 1, we'll be making use of the factorial array fact of this one, FACT, size n plus 1, and all other arrays are this one, big of logarithmic n or constant. So overall this one space complexity would lead to big of n, right? So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n and big of n respectively, right? So now as we are completely familiar with the approach and the complexities part, so we are good to write the code. Let's start writing the code, right? So I'll just come here. So we'll be making use of the this one, fast input and the output, right? So I'll just import the this one, input output package. So I'll just go with so so let me go with different, we'll be making use of different utilities as well. So let's go with a util.start. Now let's go with a main class, or let's go with some class. You can just give any class name. I'll just give main here. Just give any class name that's relevant to the question, right? So first, as per the question, let's go with the modulus, nothing but they have given 10 to the power of 9 plus 7, right? So let me go with here static final, this one int mod equals 10 to the power of 9 plus 7, right? The 8 zeros, 6 7 8, so this one 7, this is fine. Now let me go with, so here we have to go with the n m and t, n m and top, right? So n is nothing but the input, m is nothing but the floor of log 2 n. This we have considered, this we had discussed in the this one, what do we call, approach, and top is nothing but the number of multiplicative steps, right? So I'll just go with static here int n comma top. So this is fine. Now let's make use of the, or let's go with the array. We have to go with the array to hold the multiplicative step, right? Mostly 2 and maybe 1 3, right? So I'll just go with here static, so int I'll just give here var equals new int of 40. This is fine. And again, let's go with the prefix products of the chosen per sequence, right? So this one has to be static here, long. So this one, let me consider pre here, new long of, let me consider variable 40, sorry, size 40 here. This is fine. Now let's go with the factorials modulo mod up to n, right? So I'll just consider the fact here, and sorry, static here, long. So this one, let me go with fact. Again, let's go with the DP table. We will be going with the DP table, right? So for that, let me initialize the DP array here. So this one long DP. This is fine. We are just going with the DP table here. We only use DP of I0 here, right? So, but here it is allocated as 2D. That don't get confused here, right? So this is it for the initialization part. First step would be let's go with the fast modulo exponentiation, meaning a to the power of b modulo mod, right? So for that, let's write the this one helper method mod power, right? So this is nothing but the static long mod power. So this is basically problems on DP involving number theory, right? So we are performing DP with the number theory basically. Right, so this one will be long A along with B, right? So this is fine. Now let's go with the result accumulator. So this one will be long result equals 1. So while b greater than, sorry, let me go with while b greater than 0. So within the while condition, what we'll be doing? So if b and 1, if it is equivalent to 1, then result equals result into a modulo mod. So this is fine. So I haven't, we have, oh, this is the reason it was not showing in the this one suggestions. Node I have given instead of the mod. So this is fine, man. So we are just multiplying when low bit is set, right? So now let's go with a square base. Square base in the sense a equals a into a modulo mod. So this is fine. Now after going with the square base, let's go with the shift component here. Let me go with the right shift component here. This is 1. So finally what I'll do, let me return the result. So this is fine now. Now let's go with the modular inverse via Fermat's little theorem, right? So mod is prime. So we had used this one while we solved the some problems on the this one number theory, right? So you can just check that particular playlist as well, right? So let's go with the modular inverse via Fermat's little theorem, right? So mod will be prime here in this case. So just for the optimization purpose, so this one I'll just go with long inverse. So let me go with the parameter x here. So within the inverse, this one helper method, so let me go with a return here. Let me pass mod power helper method here. This one will be x comma mod minus 2. So this is fine, man. Right, so this is fine. Let me come out of this one helper method entirely. So now we have to go with the number of integers and 1 to n that is divisible by x. Nothing but let me go with some random name, calculation or calc, something like that, right? So I'll just go with the static here, long calc. So this one, let me pass here this one parameter x. So within this method, if x is 0, then we have to return 0, meaning, so we have to safeguard here calculation of 0 will not be meaningful. So in that case, we have to return 0, right? So if x equals 0, then we have to return 0. This is fine. Now let's return n by x, right? So this one will be n by x. So we are done with this method as well. Now let's go with the main method, man, right? So main method. So let's see, there are some of the helper methods that we have to make use of. So let's see, first let's start writing the main method. So I'll just go with main here. Let me delete this one. So let me include here throws exception. So within this method, so let me go with the buffered reader. Buffered reader br equals new buffered reader and new input stream reader. So this one will be system dot in. This is fine. This is for the first input. So let me assign n2. So we have n that is given in the input, right? So let's go with the input output part. So which is of the type integer. So integer dot pass and here. So let me pass here buffered reader dot this one read line. This is fine. So we are just reading the end here at the first line itself. Now we have to compute the maximum number of times we can multiply 2 while staying less than or equal to n. That's what we need to do. So if you remember floor of log to n, right? So that itself. Now let me assign m2. So let's convert this one to the integer. So again, as I have said, this will be math.log of n by math.log. So we are going with the 2, right? Log 2 basically. So this is fine. Now let's do one thing. We are going with the floor log 2 and this is fine. Next, let's allocate the factorial array. So I'll just go with the fact equals new long of n plus 1. Safer side, we are considering n plus 1. 0 factorial is equivalent to 1. We know this one, right? So let's write that one in the form of code. So base case, right? So this one will be fact of 0 equals 1. And also let's go with the for loop now. Let's pre-compute the factorials. In the sense, I'll just go with for int I equals 1, I less than or equal to n. So this one will be I plus plus. Also iterated value of the factorials. This one will be equivalent to fact. This one will be I minus 1 into I. So this one modulo mod. So this is fine. We are just pre-computing the factorials here. Let's do one thing now. Let's initialize the top in the sense we will be going with the number of factors that we have to consider or we will consider. So let me initialize top equals 0 and then let's move on with the iteration part. So this one will be int I equals 1, I less than or equal to n, I plus plus. So we'll be going with per top. So this one I'll be assigning this one to the 2 because we have to push 2m times into the per array, right? So that's what we are doing here. Now let me go with the simple if condition here. This one will be 1. As we had made use of the long, we have to go with the L here. Left shift operator bitwise left shift operator, this one m minus 1 basically. This is fine. Into 3, this is also fine. Less than or equal to n, then we have to go with again less plus this one top. This time we assign this one to the 3. This is fine. Right, so we are done with this part. Now let's do one thing. We have to go with the final answer accumulator as well. So I'll just go with answer equals 0 and we have to sort. So I'll just go with arrays dot sort. What are the things that we need to include here? Per 1, also top plus 1. What we are sorting here, we are sorting per 1 to top basically, just to start with the lexicographically first permutation, right? So don't get confused here. So why we are making use of the sorting, you can just ask yourself. So what is the reason to sort here? So basically just to start with the lexicographically first permutation, we are sorting per 1 to top, right? So this is fine, I believe, right? So if you get this thing, what do you call, if you're confused here, now let's iterate over all the distinct permutations of the multi-set, meaning per from 1 to top, right? So within the array. So let's do one thing. I'll just go with do here. So let me assign pre. So this one has to be pre of 0 man. Let me assign this one to the 1. meaning we are going with a prefix product base here. Also we need to build the prefix products, right? Nothing but I'm saying this part, pre of I equals product of per 1 to I modulo mod. So that's what, so we have to go with the iteration and mention this one. So this one will be for int I equals 1, I less than or equal to m, I plus plus. So this one will be pre of I equals pre of I minus 1 into, we have considered p, right, per of I modulo. So let me give mod here. This is fine. Now comes the dp part. So we are done with this. So we have to go with the dp dimension m plus 2 by 2. Why we have to go with the m plus 2 by 2? Because we will be making use of column 0, right? Also dp of I0 stores the combinatorial count for the first I steps. We know this one, right? So first let's go with the initialization part and then let's move on with the further steps. So first dp equals, let me initialize this one to the new long of, this one will be m plus 2 and 2. This is also fine. Now dp of 0 0, so this one will be equivalent to factorial of n. This is fine. Now for each step I, let's compute the multiplicative ratio mul mul and update the dp. So let me go with the for loop here. This one int I equals 1, I less than or equal to m. So this will be I plus plus. So within this for loop, so we have to go with the number of elements that is divisible by pre of I, but not by pre of I plus 1. So this one we have to keep in mind. Number of elements divisible by pre of I, but not pre of I plus 1, right? Also we will be going with a calc of pre of I that counts multiples of pre of I, and we'll be going with calc of pre of I plus 1 that counts multiples of pre of I plus 1. Let's try to calculate the same thing, or let's try to implement the same thing in the form of code. Sorry, yes, I'll just go with long mul this one. Let me go with calc here. We have already written the calc method, right? So this one will be pre of I, this is fine. Pre of I minus cal, so this one will be pre of this one I plus 1. This is also fine. Plus mod this one modulo mod. This is fine. Now we have to divide by n minus calc of pre of I plus 1 to convert the count into probability, right? So we have to implement modulo mod using mod inverse as well, right? For that, so let's do the same here. So this one will be my mul into inv. I have already written inv, right? So this one is fine. N minus, so let me go with calc. So we have not written the calc method. We have written the calc, yeah, inv we have written. This one mod power method also we have written. Yeah, this is fine. I got confused with the calculation part. So this one will be n minus calc of, so this one has to be pre of I plus 1 I plus 1 modulo mod. So this is fine. Now we have to multiply dp value by this ratio. So this one will be dp of I0, dp of I minus 1 into 0, this is fine, into modulo mod. So this is fine now, right? So let me come out of this one entirely. Now I'll just give here answer equals, let me go with answer plus dp of m 0 this one modulo mod. So this is fine. Let me do one thing. We are making use of the do while loop here, right? So I have written do. Let me go with the while. So I have to just pass the next permutation here. For the next permutation, so we have to generate the next permutation of per from 1 to top, right? So this one we have not written yet. So let's write that one and then let's come here, right? So let's write that one. Let's write that helper method first and then let's come here, right? So let me go with here static boolean. So this one will be next permutation, right? So permutation. So let me pass here a l as well as the parameter r. So this is fine. Within this method, let's go with this one iteration directly. So I'll just go with for and r equals I equals r minus 1. So reverse iteration, right? I greater than or equal to l, I minus. This is fine. So did I give this one? Instead I gave underscore, I believe. This is fine. So within the for loop, let me write some simple if condition. If a of I, if it is less than a of I plus 1, then if a of I means the value, the current value is less than the next value, then we are assigning j to r, right? So basically we have to generate the next permutation of the per from 1 to top, right? So this one, let me assign the j to r. This is fine, we have already done that one, right? So let me go with the while loop here. While a of j, if it is less than or equal to a of I, then let's decrement j here. This is fine. Also let me go with swap basically, right? So for swapping, again we have to write the this one, what do we call, we will be making use of the swap and reverse within the method with a swap and reverse methods within the next permutation. So swap utility, let's write that one helper method, right? One more helper method. For the reverse also, let's make use of another helper method, right? So I'll be directly making use of it. Don't get confused here. So this is not some operation, right? So this is not some data structure operation or something that comes up directly, right? So this I'm considering here. I have not yet written the swap helper method or the function yet. So we'll be writing that one in the future. I'm directly using it, right? So I'm just stressing on it. Don't get confused here. So this one will be a comma I comma j for swapping. So this is fine. And also for the reverse as well, we'll be writing reverse helper method as well. A comma I plus 1. This is also fine, comma r, right? So this one, let me return true here, else we have to return false, right? So let me return false here. This is fine. Now let's go with the swap utility here. So I'll just go with static here, void. So this one swap of int a comma int I. So this one will be int j. This is also fine. Now within this, I'll assign t to a of I. Also let me assign a of I to the a of j. Also let me assign a of j to t. So as we are swapping here, this is fine. This is also fine. Now we are left with reverse. So swap we have I have already written this one. This is fine, we have already made use of it within the next permutation. Now we have written the swap method as well. Now we are left with only one thing, reverse, right? So we have to write the reverse method. We have not written that one yet. So this is the reverse utility for array segment, right? So I'll just go with static here, void. So let me go with reverse. So this one will be int a comma int l comma int. So this one has to be r. So while l less than r, so this one let me go with swap of a comma l comma r, right? So this is also fine. We are making use of swap within the reverse method. And so let me increment left and decrement the right, r minus 1. This is fine. We are done with the helper method reverts and swap, right? Also the next permutations as well. So let me copy this next permutation and let me come to the main method. So we are making use of the do while loop here, right? So we had stopped here, so we will be making use of the helper method next permutation here, just to generate the next permutation of per from 1 to top, right, within the array, right? So this one will be, I have to pass here per 1 along with the top, right? So this is fine one. Now let's do one thing. So let's print the final result modulo mod, right? So let's print the final result modulo mod. So I'll just go with println system out println. So let me pass answer here. This is fine. We are done with the coding part, man. This is it for the coding part. Simple, right? So now before checking the code with different inputs, let's do one thing. Let's quickly this one copy paste the signature starter template. Just give me a second here. So I'll just come here, I'll just paste it over here, right? So this one, I just consider the output that we need to get here is 1, right? So I hope we get the output 1. Let's see. We are having the error here in the line number 33. Just give me a second here. 1 second. So yeah, what error we are having? B7. This has to be ampersand. So yeah, going with the modular inverse. This is bitwise AND here. So this is fine. Now if I run this, yeah, some of the errors are gone. Still 5 errors left. So this one has to be into here, right? So multiplication into inverse of this one, line number 75. Where is it? So this one, let me make this one to the into. So this is fine, multiplication operator. Now let me run this one again. So we are left with 3 errors. Answer 79. Just now we have written this one, right? What is the error? 1 second. Oh yeah, I have given 5 here instead of modulo mod. This error has to be gone as well. So we are left with this one, L plus plus. So yeah, we have to give this one here semicolon, not the comma here, right? So this is not JavaScript, this is Java, right? So this is fine. We are getting the output 0, man. We have to get the output 1, right? So here if I copy this one, let's see for the second input. So we are getting the 2 instead of 4. We are getting the wrong answer. Let's check what is wrong here. So what mistake I have done here is in the line number 60. So we have to go with the per array, so not the pre, basically. That is the reason we are getting wrong answer, I believe. So let me run this one. Yeah, now we are getting the output 4. So this was wrong actually. In a hurry I had typed pre rather than the per. So the variable that we variable name that we have given is per, not the pre, right? So this is fine. Now let me check with the first one as well. So we are getting the output 1. This is correct, right? So let's check with the last input. So we have to get the output 120. Let's check. So we are getting the 120, right? So the code works absolutely correct in this case. So let me come here, let me hit the submit code. So let me choose here, this one is E, right? So yeah, problem E. So let me paste the code and let me hit the submit button. Here you can clearly see running on test 1. Let's wait for some time. So yeah, you can clearly see here, right? The verdict that we have got here is accepted, which means the code, whatever the code that we have written, works absolutely correct for all the test cases, right? So we have So we have made use of the DP here along with the modular inverse, right? So also we have made use of some helper methods as well, right? So here swap, this one, reverse along with the next permutations as well. These are some of the helper methods that we have made use of. We can just directly write it, but on the main function the code would have been this one, difficult to read. That is the reason I chose this way, right? So this is easily readable code, and we can understand this code in a easy way. So this is fine. Now I hope the coding part is completely clear, man, right? So I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.